Welcome to the Math Record. Today we'll be learning about the dot product. This video will cover part 3 of chapter 9 of our Precalculus class. In this video, we will explore the dot product and their properties. In chapter 9 part 1, we learned how to add and subtract vectors. Now we're going to learn how to find the product of vectors, which is referred to as the dot product. So let's say we have vectors u, a, I plus bj, and vectors v and vector v, which is ci plus dj, right? The dot product, which is just u times v, is equal to a times c plus b times d. Don't write u times v. There's actually a different note. Vectors have a different notation. So when you write u times xv, we're gonna be covering this in the future video. It's gonna be called the cross product, which is different from the dot product, which you use a dot. So don't mistake it. It might look like a multiply sign, but just make sure that you're doing it right, basically. And usually when you want to like multiply factors, you actually have to put that dot, so people understand your correct notation. So for example, let's say u is equal to 2i plus 3j, and v is equal to like I plus 4j. Then u times v is the same thing as like 2 times 1, which is 2, and 3 times 4, which is 12. So that will be the dot product of vectors u and v is 14, basically. So that basically is the general idea for dot products, like how to multiply like two vectors. It seems strange because now there's no i's and j's. It's just going to be some kind of number. Okay, so let's move on to their properties. These also follow arithmetic rules, and there isn't that much about it. So if you have a dot product of u times u, u and v, it's the same thing as v and u. Because remember how it was? It's just a times b plus a c plus b d. Well, it's the same thing. So if you like, it just multiplies the x together and multiplies the y together. So it doesn't matter which way you put u's and v's, because it's just gonna be the x multiplied together and the y multiplied together. And then another product is that u times u dot product of v plus w, where v and w are also vectors. It's the same thing as u times v, u dot product in v plus u dot product in w, so you distribute it out. So that is another property. And that's basically like the only two properties that really matter. So if you understand those, it's really basic. It seems like the arithmetic rules all the time. And next up is how to like find the angle between two vectors. Angles of two vectors. So let's say you have a graph like this, and then you have a vector and another vector. You want to find the angle between them, which will be denote as theta. There's a really simple equation on how to do this. Now that we have the dot product, it's really easy. So this is just cosine of theta is equal to the dot product of u and v divided by the magnitude of u and multiplied by the magnitude of v. U and multiply the magnitude of v. Okay. So let's have an example like u is equal to 2i plus 3j and v is equal to 1i minus 4j. So the dot product is u times v, so 2 times 1 is 2. And 3 times negative 4 is negative 12. All over the magnitude of u, which is 2 squared plus 3 squared, which is 19. So square root, 13, square root 13, times 1 squared plus negative 4 squared, so that's 17. And cosine of theta is equal to that, basically. So we have, using our calculator, 2 minus negative 12 is negative 10. And square root 13 times square root 17 is, and then you -10 divided by that number, and then you just use inverse cosine of that, get you your degree sign, which is equal to about 132.3, sorry, 132.3 degrees is. So which you would just like draw the picture of. So you have like 2, 3, so you have something like this. And you have 1, -4. So it looks like something like this. So like the angle between them, like right here, is 132.3 degrees. Because you could just think about which one's the smallest, because this one's like a little bit bigger-ish. So this one is 132.3 degrees. So that basically covers like how to find the angle of two vectors, which is really simple. It's just the cross product divided by the cross product of both the vectors divided by both magnitudes of the vectors. The cross product also tells us that if we have two vectors like v and u and v, if u is equal to like a v, or v is equal to a u, and like it's like this exists, then the two vectors are parallel, which sounds like kind of pretty obvious, right? Because let's say you have u is equal to like I plus j, and v is equal to 2i plus j. I mean, if you graph it out, it's just like one here, and then the other one is just a little bit bigger, right? So it's just parallel. It's just that they have different magnitudes. And it also, and the other property that's really unique is that if the dot product uv is equal to 0, or v times u is equal to 0, since we said it's the same. If this is equal to 0, then it's perpendicular. The vectors are perpendicular. So you have something like this, and you have another vector, and if these multiply to dot product is 0, then it's gonna be 90 degrees basically. So because they're perpendicular to each other. This is it's also referred to as orthogonal. Orthogonal. So they're perpendicular to each other. Okay. Now let's actually learn about let's learn about vector projection. This concept is basically to make vectors that's orthogonal from one vector to like reach another vector. So imagine you have like a graph, right? And you have one vector like here on the x-axis, and you have another vector that's like a diagonal. What you and we say this is v and this is u. Then a vector projection would be like if we made a line, one vector right here, we'll call that v1, and this is v2, and this is still v, and this line is still vector is still u. Then there's gonna be one vector that it's parallel to u because it's gonna be on it, and one vector that's perpendicular to u because it's called v2. So we'll call then v1 will be called the vector projection of v onto u because it's parallel to u, and that's the idea of it, to make like a vector that's parallel to like some kind of vector, but then like also perpendicular to it, so it could reach another vector basically. So let's try like a practical example. Let's say we have like an object that weighs 100 pounds, right? Um, sorry, we have an object that weighs 100 pounds at a ramp of 30 degrees. So how much force is needed to keep like the box still? So instead of using like our idea that we use like force vectors, now we could use the concept of vector projection, which follows a really uh kind of strange formula. So let's say you have vector v, right? And we have vector u. then the vector projection of v onto u would be equal to, let's say, the first vector, which is parallel, which is v. The vector projection was v1 is equal to v times u, which is the dot product of v and u, divided by the magnitude of u squared times u. So that'd be our vector projection. And then the opposite one that is perpendicular, we'll call that v2, it's equal to it's equal to just v minus v1, which is the vector projection. So that would be the basic concept. So if we have vector projection of v onto u, this would be the parallel, v1 would be parallel to u, and v2 would be perpendicular to u that reaches v. So if we have some, like an object that weighs 100 pounds, right? Sorry, we have, so the question is, like, if an object weighs 100 pounds at a ramp up 30 degrees, how much force is needed to keep the object, like, still? So we have a force that's going down on it by 100. Sorry, oops. V minus V1. Sorry about this. I'm trying to delete it. I just don't like using the eraser. Okay, good enough. We have something that's like 100 pounds, right? And now we're gonna we have this force going here, and we have the force that we don't want to, like, we have the object, right? And we don't want it to go down. So we had to think about how this works. So we have a force projection of this force, which is V, onto U, basically. So it has to be parallel to this line, but we want to get to this, like vector. So we have this vector, which would be 100j, well, negative 100j, because it's going down. And the vector here, since it's going down this way for the object, you have to have another force with equal like magnitude. So then it would be like staying still. You get it? Like there's a force, and then you combat it with equal force, so it doesn't do anything. So we have force 1, which is V, which is just negative 100j, and U, since we know this is 30 degrees, right? We would just say that is cosine of 30 times I have I plus sine of 30j. So we have that. Let me move this picture up a little bit. So we need a little room. I'm sorry that we can't see the picture. So basically, now we just find the dot product. So v times u. So there's no I, so 0. So this is 0i minus 100j. So 0 times cosine 30 is 0, basically. And negative 100 j. So negative 100 with the j here. So which is equal to cosine of 30 is 1/2 times 1/2, because the dot product is just 100 over 100, negative 100 times 1/2, because that's what it is. And now you have the magnitude of u. The magnitude of u is cosine of 30 squared plus sine of 30 squared, which is just basically 1, because that's the Pythagorean identity for sorry, for trig, for trigonometry. And then you multiply by the vector u, which is just this, which is just cosine 30i, sorry, plus sine of 30j, right? So this is negative 50. So the v1 is equal to negative 50 negative 50 cosine 30. Cosine 30 is square root 3 over 2. So this is negative 50, right? So this is negative 50. This is square root 3 over 2. And this is 1/2. So overall you get negative 25 square root 3 um for the force for I, and then a negative 25 for J. So let's delete this and move this up. Right. And now we just need to look for vector. This is the vector that is parallel to the U, which makes sense. And now we have vector 2, which is just the original V minus the the vector projection, which is just a negative 100J minus 25 square root 3 over 100. So this is just 25 square root 3 I, because negative of a negative positive, and then minus negative 25 was plus 25, so that's so negative 100 plus 25 is negative 75J. So that would be our vector projection. So in our picture, it will look like this, right? So now we have the vector projection going this, and then the force that's needed to push up is this way. So what we have is basically we need to find the vector projection will give us basically the force we need to push it. So what we really didn't have to calculate the entire thing, but I just want to show you the vector projection how it worked. This would be the force that that was needed to keep the object still. So the because that's the magnitude, that's the magnitude, and you already have it in the form polar, so you just need to find the magnitude. So it would just be negative 50. So the for the force required to keep the object from staying at that place is just 50 pounds. But most commonly, I wouldn't be using vector projections to find like the force. I would just be using the force vectors, which is faster and more easier instead of using all these like like operations. Um, the dot product could also be applied to physics concepts like work. So imagine so imagine you had to push like I don't know, like a small box across the floor versus pushing like um like a closet. The closet will be harder to push because there has more. Yeah, there's more work to be done. That's like a basic idea of like how it works. So work is equal to the magnitude of force times this distance, basically. So work is measured in foot per pounds, or it's measured in newtons per mile. I mean per meters, which is also known as joules, as you might have been learning. So this will calculate work. So let's give an example. So imagine you have a 100-pound object. Um, you have to move a 100-pound object 10 like feet at a 30-degree angle, right? So basically, what you do is so you put this in polar form. So the object would be 100 cosine of the angle, which is 30, plus I'm I mean I plus sine of 30 of j. So this would be our the force, because we need to find work is equal to magnitude of the force times the distance, right? This is what we need to find. So we already got the distance, which is 10, right? So we just need to find the force. So this one will give us the force basically. So we have force is cosine of 30 is square root of 2, and sine of 30 is 1/2. So this kind of simplifies out to 50 square root 3 I plus 50j That's our vector. For our force, well, sorry, I'll just write it as F so it'll be easier to understand right now. So, now we just need to find basically the magnitude of the force times its distance. So we have times 10. So you just basically have this times 10, you know? So we have I mean, sorry, it's the force vector times the dot product. So the dot product is 10. So the distance is 10, which is just since you're moving in the horizontal direction, which is just 10I plus like 0j because there's nothing there. So what you do is that you just multiply the distance kind of together, you know. So you have 50 square root 3 times 10, which is just 500 square root 3. So the amount of work is just 500 square root 3 foot pounds because you're using in feet and you're carrying it in pounds. So it's just called it used in foot pounds. And that's basically the general idea of like how it works. So in summary, today we learned how to like multiply vectors, which is known as the dot product, and learn how to find the angle between two vectors, along with like how to find work, which could be applied to finding work. So anyways, thanks for watching, and I'll see you at the next math record.